Welcome back, everybody. We are going to continue. Before we continue, I will summarize again what we've done last week and in the first hour today in order to give meaning so that you know why we are doing all of that. Again, the point of data modeling and data frames and schema validation is that when you have a data set downloaded from the internet in a textual format, if you are able to create a schema, validate it against that schema, that allows you to turn the whole data set into a data frame. And as soon as you have a data frame, you can save it in a binary format. And it means that you just downloaded 1 terabyte of JSON data, and now you have it all in 10 gigabytes of Parquet. This is how powerful this is. So it's theoretical, of course, but this is of very practical use to data scientists because it makes a huge difference if you are able to compress the size to 100 times less in terms of performance. Because that really means that you can analyze the data in 6 minutes instead of an hour, and that does make a difference to the user. Okay, so now, because I said we query the data, so let's query the data, right? Because we've spent already 7 weeks not querying any data. We've just looked at data so far. So now we can start querying it, and massively parallelly, we'll query that data. So this is where we are. We already covered a lot, right? We are halfway through. And hopefully you also understand why we covered all of that. But now we are moving on to processing the data. So I know it's the morning, it's 8 a.m., so we'll need to wake up. So let's do it in a fun way. Last weekend, I went for a Pokemon hunt, and I collected a lot of Pokemons. But the thing is, I want to count them. I would like to know how many Pikachus I caught and so on. So I could, of course, do it manually, right? And just count them one by one, keep track and so on. But the problem is that when I do that, it actually takes me 2 hours. And so I thought, we actually did it in the fall. Now, in the interest of time, we cannot do it in the lecture, but with the master students, we did it inside the lecture. I would like to know how many of each I have, and the way that we typically do it in the lecture hall is that I had these huge bags of Pokemons that I brought, and then I asked for a few volunteers, students in the room. They each got 1 bag of Pokemons distributed to the volunteers. And the idea is that every one of these volunteers is going to take the Pokemons from their bag, and they are going to count them and write it on a sheet of paper. In that case, 2 Pikachus. I have a huge difficulty with the names of the Pokemon, so I'll just stick to 2 Pikachus and so on. Yes, so that's basically the output of this first round of volunteers. We write it down on a piece of paper. And then we need a second round of volunteers, so other students. They are going to do something different. These students will be responsible for a few Pokemons. So for example, here we have Alice, who is responsible for Pikachu. And what happens is that the students from the first round who wrote down the intermediate results like this on a sheet of paper, they cut you notice that these are key value pairs, right? These are key value pairs where the key is a Pokemon and the value is an integer. So they cut them with scissors like this, like key value by key value. And the idea is that all of the key values that correspond to Pikachu that came from several different students from the first round, they go to Alice, right? So I must say, when we do that, it's a bit of a mess because you really have to understand that there were plenty of students running around trying to carry over the right Pokemon to the right person and so on. But the fact that it's a mess is part of the whole thing, right? It's basically that's what we call a quadratic complexity, because every volunteer from the first round has to meet every volunteer from the second round, right? So this is something that takes a bit of time. But in the end, basically, Alice will receive all of the key value pairs where the key is Pikachu. What does she do? She adds them, right? Takes all the numbers, computes the sum, and writes back her output here to 8. Now we have 8 Pikachus. And now if every everybody else from the second round does the same, at the end, I will get my final results. Who agrees that this is a correct way of computing the number of Pokemons? Right? Okay. Now, what's nice is that this takes 20 minutes for something that would have taken me 2 hours to do. So it means that there is an improvement. Where did we get this improvement? It's because many people helped me out, and I was not alone. So the whole thing is the parallelism. It's the fact that all of that here, this phase happened in parallel, several students at the same time. This is not really, this is kind of the huge mess, right? But then this happens in parallel again, the counting. What you see here, what I have just described, has a name. It's called MapReduce. Map because this is technically a mapping from the bag of Pokemons to these Pokemon integer key value pairs. This is a mapping, map. And this is called reduce because you take all of these intermediate Pokemon value pairs, and then you output a single Pokemon value pair, right? So this is reduce. The part in the middle, you know how it's called? It's called shuffle. So this is the shuffling of the Pokemon value pairs between the students, right? So technically, I think a better name would be map shuffle reduce to really do justice to this intermediate messy period in the middle, but we just call it MapReduce. Who had already heard of MapReduce before? Some of you, okay. Because that was it was a buzzword back then. I mean, now it's probably almost 20 years old, but it was like the artificial intelligence and machine learning and blockchain of the time, right? This is like MapReduce, MapReduce. Everybody wants to invest in MapReduce. So this was a big thing. During the, I actually did it last year for the first time to show the sort, because of course here it's human beings who did it, but in reality, we are going to use computers. And what happens is that it looks like this. You basically have the status during the map phase. So this is map, 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 map. It's a completion bar. Then at some point, the shuffling will start. And then the reducing. And now we're complete, right? So this is how it works. I said that it has to work in parallel. So you probably already guessed that instead of happening on your laptop, this is going to happen in a data center. I'll come back to the laptop because you wouldn't imagine that we can also do things in parallel on your laptop. But let me start with the data center. We already introduced HDFS, right? The Hadoop distributed file system. It allows you to spread data over 1,000 machines. In fact, that is a great basis for MapReduce because the data is already distributed, so we can just read it in parallel already where it is. So we can use a file system like this. So before we move on, let's look at that file system. Imagine we have HDFS, an instance somewhere. What kind of data do we have on HDFS? Well, now you know what kind of data we have because we spent 7 weeks on that, right? So now I can tell you what kind of data we have. Maybe the kind of data we have is, sorry, clicking too fast. One back. If I click again, it's going to come 2 back. You see, it came 2 back. Okay. So maybe we have huge quantities of text, right? Now it's actually quite fashionable with ChatGPT and training on the huge quantities of text. So yes, you could absolutely have this in HDFS. This, in that case, is Sherlock Holmes, if I'm correct. Now it's public domain, so you don't even have any licensing issues. Of course, you heard with ChatGPT the licensing issues. It's quite tough, and there are even disputes, for example, with the New York Times and so on. I didn't take that risk. I just took something that is public domain here, so that is in there. So you have to imagine billions of lines stored in HDFS. And billions is quite reasonable for HDFS, right? We have so many machines that fits. Or we could have CSV files. Maybe I could have billions of lines like this in my CSV file that it's a bit more structured, right? There are commas. Who sees a table here? you should all see a table. Everybody should see a table here, right? It's CSV. So you have a table with the year, the first column, then the date as the second column, and duration as the third column, and guest as the last column. You know what this is, right? This data. It's the Zurich measures. So obviously, we've been doing that for as many years as the universe. So you have billions of lines in there. It could be also, you know, in that case, it's CSV, but it doesn't need to be CSV, right? It could be also some more raw formats that it's not any particular syntax. This kind of syntax is actually quite popular in meteorology, climate, weather, and so on. So Météo Suisse, like this kind of institutions, when they accumulate sensor data, it's very often that it's in that format rather than CSV. Why? Because you save some space with the commas and so on. You know exactly the reason why it's done that way is that you know that the year is exactly the first 4 characters. You know that the date has exactly a fixed number of characters. So if you know exactly where to cut, then you don't need the commas anymore. So this is also a technique to save a bit of space. It's not going to save as much space as a binary format, but everything you can get as space is worth it. So this is another kind of format. It's still text, right? You also have some convention that you can have a key value format in the text, but it's really just a convention. The idea is that you just use some character that you agree on. In that case, it's a space. Whatever is in the left is on the left is a key, and whatever is on the right is a value, right? So it's a key value format. It's pretty rudimentary, right? Pretty simple. But again, the idea is you have keys and you have values, okay? But this is still text, right? At that point, we just look at text. Now, technically, this is still text also. This is also text, but that text is not any text. It's well-formed JSON, right? It's a very common way to actually store JSON. Every line of text here has one JSON object. This is called JSON lines, the standard for that, JSON lines. Every line is a well-formed JSON object, okay? This is also something you can and will have on HDFS, right? So billions of lines of well-formed JSON. You see the format as well here, right? You could come up with a JSON schema here, year integer, date, duration. Here you would need some union between some time, for example, time and null, and the content would be string, for example, right? And date is optional, and content is optional. Right? So you could come up with a schema that takes care of that. But basically, as it is, this is just JSON data. It could be binary. We could have, in fact, petabytes of binary data. When I say binary, what do I mean? Well, it could be images and videos. Maybe you have a large model that trains on pictures and videos, right? But that could also be Parquet. That binary format here might, in fact, be the same data as this, except that somebody went through the effort of validating these objects, creating the data frame, saving it as a Parquet file, and then it takes much less space. But this also goes to HDFS. You can have JSON, you can have text, you can have Parquet, you can have anything you want. So these are a few examples of the sort of things you can have, right? So you see everything you've learned so far. That gives you already so many possibilities of what you can store on HDFS. And by the way, I say HDFS, but it could also be S3, it could also be Azure Blob Storage. You know, any of these just will do, right? Even the Google Cloud Storage works as well. Okay. Now, here's a trick that I've already talked to you about. Technically, when you have petabytes of data or when you have a file, a data set with billions of lines, if you wanted to save it as a single file, you could, right? HDFS allows you to do that. You can have a petabyte-sized file, and that's totally fine. But in practice, this is not what people do. And the reasons are very practical reasons. Is that, first, it's extremely difficult to upload very large files to HDFS. Because of network issues, it's going to cut in the middle, then you have to start all over again and so on. So there are many different practical reasons why people do not actually directly upload very large files to HDFS. What people usually do, in fact, is that they store it over multiple files. So instead, if you have 1 billion lines of JSON, for example, instead of having a single file with 1 billion lines, you might have 1,000 files, and each file is going to have 1 million lines. This is called sharding, technically, in that context. It's sharding. And typically, the names of the files have these increasing numbers. You have basically a directory, and then there is a file called part1, and another called part2, and another called part3. You also pad with zeros in order to make it look nice and have the same character size for every file name. But this is the idea here. There's only 14, but it can be 100, it can be 1,000, it can be 10,000. So technically, if you look at HDFS, a very typical setup is going to have in the same directory plenty of shards of the same data set. And again, every one of these is a file. Right? Again, I told you all these synonyms, right? Here it's called part, shard, chunk, block, split, partition. There are so many different synonyms. They are used a bit interchangeably, but that depends on the context, right? Again, in that context, we would call it a shard. The names of the files, they usually use the word part. Block would be in the context of HDFS, chunk in the context of the Google file system. I mean, it really depends on the context, but they really mean the same thing. It really means that you divide something that is big into many smaller parts. Okay, so this is the sharding, the way we shard the data sets as is commonly done. This is true for the inputs data, and it is also true for the outputs data and the intermediate data that you might generate. It will also be typically organized in this way as shards. Okay, so this is one way of putting it in HDFS. You could also use HBase because why did we learn HBase if not to use it? So you could also use HBase in order to execute queries on top. That's absolutely fine too. And then you also have the notion of parallelism because you have all of these regions in HBase, right? So you could also work on the regions in parallel, right? So it's perfectly fine as well. And the regions are even distributed all over the cluster, right, on the region servers. So HBase would also be a perfect match as the to read the data from for MapReduce. So since we are at it, HBase, that would be more like a two-dimensional format or a tabular format, it works as well. We could have billions of rows, and we could also want to execute some queries on top of that, right? In that case, that would even be a relational database. It's even possible to do it with a relational database, these kind of things. But since we use HBase and a white column store, we might even have XML inside, right? So typically, we could have, I told you, right, in HBase, you can store typically up to 10 megabytes of data in the same cell. So we could use the HBase cell of a table to put an XML document. So you see what I did here. It's really an application of what we've learned. I have an XML schema that you see here, occurrence, year, date, duration, canton. It's the same Zarsiluter data. That's an XML schema. And if in every cell, in every row of my table in HBase, I have an XML document that is valid against that schema. That is one way that you could use HBase. You could absolutely store XML in that way. You could also think of just like JSON lines, some sort of XML lines format, but this is not what people do. That doesn't really exist. You could, if you wanted to, have one XML document per line, but this is really not something people do. Instead, you would rather use something like HBase and put the XML inside cells. Okay. And once we have that, we can query the data. And in order to query the data, we are going to do it in parallel. So we are going, again, to use shards, be it shards on the files, in a directory, shards as regions in a table, and so on. And that's pretty much the idea, right? So data is in the shards, as we could say. Which brings us to the paradigm that we are going to look at, which is MapReduce. So if you look at it on a very, very, very high level, it's quite simple, right? You have some input data, you want to execute a query, and you're going to get some output data, right? So this is what we want. Now, the idea is that if we shard the data, I added these dashed lines here, right? We shard the data. So the question is, do we get any advantage by sharding the data? Now, in an ideal world, if I could have a Christmas wish list, I would wish for my query to actually look like this, right? If I actually can formulate my query in this way, this is wonderful. Why is that wonderful? Because it means that every one of the shards can be processed in parallel, and you don't even need to communicate across the shards. So the intuition here is really that if indeed it were the case that my query could be expressed in this way equivalently, then on one machine, I take that shard, execute the query, and get this output shard. On another machine, in parallel, I take that shard, query, output that. On a third machine, I take that shard, execute the query on that. And if I have 8 machines here, I can just process it in parallel. How much faster is it going to be compared to using a single machine? 8 times faster, right? Because I just do it now on 8 different machines. 8 times faster, we'll see it's not that simple, but for the moment, I'm just simplifying a little bit, right? So we can be 8 times faster by doing that in parallel. Now, this is what I would wish for, and this is reality. In reality, the problem you have is that when you want to compute, for example, that part of the output, you might need to not only read that data, but you might also need data from here. It might be that there is a dependency from here to everything in there. So it means that in the general case, you have a huge spaghetti and you cannot parallelize it so easily, right? It's very, very complex. If it's on the same machine, that's easy, right? It's all on the same machine, so you just write a computer program that does all of that. It might take a while, but it's going to work. So the question is, how do we execute a spaghetti like that in parallel on several machines, right? That's a very, very complex problem. And in fact, the insight that the people had who designed MapReduce is that reality might not be that ideal, but it's also not that bad, right? In fact, reality is more like this. It's kind of in the middle. So it means that if you look at queries, everyday queries, there are parts of the queries that you are going to be able to parallelize, that kind of naturally translate into some parallelism. And some other part, if you zoom out, so if you zoom in somewhere else, is going to be spaghetti, right? So there's the parallelizable parts and the spaghetti parts of the query. Once you have understood that there are the parallel parts and the spaghetti parts, then you get MapReduce. Because the whole idea of MapReduce is to just say, we first do some parallel parts, then we do the spaghetti part, and then we would do again a parallel part. And if we need some spaghetti again, then you just do it again and again and again and again, right? So this is one single MapReduce job, but you could have then a second one, then a third one, 10, 100 jobs, one after the other. But in a single job, you have exactly one parallel part, one spaghetti part, and one parallel part again. The first parallel part is called mapping. The second parallel part is called reduce, and in the middle, you have the shuffling. But since we've done it with Pokemons, that should be clear to you, right? What's going on, because we've already done it in real life. Okay? This is, in fact, MapReduce. It's really that simple. But what is remarkable with MapReduce is that it's not only simple, it's also generic and powerful enough that many real-life problems and real-life queries can actually be done in that way. This is incredible. This is something that it's really now, it's been 20 years that we know that. Before that, that's not really something we were aware of. But this is extremely powerful. There is a question?
We have a question online. How do I know beforehand what I can do parallel and what not?
So I will give 2 answers to this question. The first answer is 10 years ago, maybe even more than 10 years ago, let's say 15 years ago, I would have answered your question by saying that it's your problem. It means that if you want to use MapReduce, the burden is on you to figure out how to formulate your problem as a map and a reduce. The burden is on the user. And in the early days of MapReduce, this is what happened. So the users of MapReduce, they would have to sit on a table or stand in front of a whiteboard, and they would have to think, how can I formulate my problem in a way that is a map and a shuffle and a reduce? Surprisingly, you can often do that, but the burden was on you. It required a human being that actually did that. However, now we have a newer generation of database technologies, and in fact, Apache Spark is one of them. We are going to look at it next week or the week after that. And that kind of now solved that problem. It means that if you use a technology like Apache Spark, you no longer really have to deal with these things, right? So I'm still showing it to you because this is interesting to see what's happening behind the scenes. But now, in 2024, we have the luxury that we don't need to do it ourselves anymore. Now we have query languages like SQL, like JSONic that you're studying as well. And in fact, when you have SQL or JSONic, you can forget about that. You don't need to figure it out anymore. The computer will do it for you. That's really magic. And the progress we've made in 20 years is absolutely amazing from that perspective. Right. Did I answer your question? Yep. Awesome. Okay. So we have the input data and the output data, but let me also have this here, the intermediate data. Remember the intermediate data, it was the Pokemon value pairs that were output by the first volunteers and shuffled around to the second volunteers. Now, what does this input data and intermediate data and output data have in common? They are all key value pairs, or Pokemon value pairs in the case of the Pokemons, right? So they are all key value pairs. And MapReduce, in fact, requires that. In MapReduce, everything in your input must be a key value pairs. Everything you write down as output must be a key value pairs, and everything in between must also be a key value pair, right? It can lead to a situation where when you have a hammer, you tend to see everything as a nail, right? So we kind of now have to fit everything into key value pairs. It's actually not that difficult. But again, this was 15 years ago, and now with Apache Spark and the query languages, this is all hidden, right? But technically, MapReduce does require you to think in terms of key value pairs. If you have a key value pair, then you must specify what is the type of the key and the type of the value. Now you have some flexibility here because the types for the input data do not need to be the same as the types for the intermediate data and do not need to be the same as the types for the output data. However, all of the input data must have the same key type and value type. All of the intermediate data must have the same key type and value type, and all of the output data must have the same key type and value type. An example of key type is Pokemon. An example of value type is integer, right? Now, in the case of Pokemons, the intermediate key values and output key values all had the same type. In fact, it was a Pokemon and an integer. For the input, what was the input? It was bags of Pokemons, right? So these were not key value pairs. So we would have to convert them to key value pairs, but that I'll come back later, right? Okay. And in fact, what we had in the case of the Pokemon value pairs, that the intermediate types were the same as the output types, is in fact the case 80% of the time. It's not always the case, but 80% of the time it is the case that you have, in fact, the same types for the intermediate data and the output data. The reason for that is that the reduce function very often is just an aggregation over the values that have the same key. That's the reason. So a sum, for example, as is done on the Pokemon integer pairs. Okay. So we've been once through it with the Pokemons. Let's do it again, but now formally, right? We forget about the Pokemons and just look at it from an abstract perspective. So my input, again, everything must be a key value. So my input is billions of key values. How we transform any input to billions of key values, that I will get back later, but let's assume we have as an input billions of key values of any type. The first thing that happens in MapReduce is that we split this input, right? If it's on HDFS, you could use the blocks of HDFS as your splits, right? So You basically just split it. The goal of the split is to be able to parallelize, right? In HBase, that could be the regions that give you the splits. But you basically need to split that data over multiple splits. Split is the MapReduce name for a shard, block, chunk, partition, part, and so on. We call it a split in MapReduce. Okay, so we split the data. Then the second thing that happens is that every one of these key values from the input will be mapped to 0, 1, or more intermediate key values. In that case, 2, but again, it can be 0, it can be 1, it can be more. So we have a map function, that's a mathematical function, that takes one key value of the input and outputs 0, 1, or more intermediate key values. That is the mapping part. Of course, the map function specifies it for one key value, but in fact, we call that function on many, many key values, right? So in parallel, every one of these key values on the left will be mapped to 0, 1, or more key values on the right. Okay? So this is then the mapping phase in parallel. And once we have produced all these intermediate key values in parallel, we put it all together logically, right? So you imagine you have the same top that you put everything in there, right? You have billions or trillions of intermediate key values. And what you do is that I'm on the logical level, right? On the logical level, imagine that you take these trillion key values and sort them lexicographically by key and then by value. So you have all the key ones together, all the key twos together, all the key threes together. Once you have done that sorting, you can separate them again in groups, and every group has the same key. So you have a group with key 1, so all the Pikachus are there. You have a group with key 2, a group with key 3, and so on. Once you have these groups, you're going to call on every one of these groups the reduce function. The reduce function takes one group of key value pairs that have the same key, and it must be all the intermediate key value pairs that have the same key, all of them that have key 1. And that reduce function outputs 0, 1, or more output key value pairs, final key value pairs. In that case, is 1. It's very often that it's actually 1, but technically it could be 0 or it could be more. Okay, so we have that reduce function. Of course, this is one group, but there are several groups, so we do it in parallel. Very often, as I said, the key types will be the same, and what the reduce function does is just a sum or a max or a min on the values, right? And it keeps the same key. So 80% of the case will look like this, but generally it will be more like this. And again, it can be more, it can be 0. I mean, this is fully general. It's just that it's less often that you would see this. And again, this is done in parallel, just like the mapping phase. I told you both the map phase and the reduce phase are in parallel. So we have this mapping, and on the right, you have all these output key values, and that's it. So if I draw now everything, you have the input part to remove this on the lecture hall because that prevents from seeing. You have the input part. You map to intermediate key values, you sort and partition so that the keys that are the same are in the same group. Then you call the reduce function on every group, and then you get 0, 1, or more output key values for every group. That's your final output, and you write it back to HDFS or to HBase or wherever you want. Okay? So this is the logical part. Who is with me on that? Okay. Think of the Pokemons. If you're ever lost or map, shuffle, reduce, just think of the Pokemons. This is the way to go. Now, what's really nice is that the architecture is flexible because you can execute MapReduce on top of HDFS, but you can also do it on top of S3. You can also do it on top of Google Cloud Storage, Azure Blob Storage. In fact, you can even do it on your local file system on your machine. And you can even parallelize on your machine. How can it be? Remember that you have multiple cores on your machine. Today, we have 2 cores, 4 cores, 8 cores, so you can also parallelize on your machine. That I'll come back to you on that, because it turns out that big data also applies to your laptop. So typically, you can have thousands of machines in your data center. You can have terabytes or even petabytes of data without any problem. And the architecture looks like this. This should be a bit like a feeling of deja vu, right? We've already seen that with HDFS, name node data node. We've already seen that with HBase, HMaster, and region server. Well, guess what? It's the same with MapReduce. We have job trackers and task trackers. These are the same machines, by the way. Name node, HMaster, and job tracker. This is a process, just like Word or a Notepad or your browser. These are processes. On the same machine, you have a name node, an HMaster, and a job tracker process. And on each one of the other machines, you have a data node process, a region server process, and a task tracker process. What's important is that these are the same machines and that it is centralized because you have a coordinator node that is kind of the brain, and then you have all the worker nodes that do the work. And again, to make even clearer that it's the same machine, you really have the name node and the job tracker on the same machine, and the task tracker and the data node on the same machine. And the idea is that we bring the query to the data, because where is the data? It's all over the place. It's on HDFS, so these are the blocks in HDFS, they're all over the place. So the goal is to try to not move the data too much. We just execute the queries where the data is. What it means concretely is that we evaluate the map function on the same machines that the data is. Where is the data? On the data nodes. So we evaluate the map function also on the data nodes, and this is what the task tracker is doing. And that way you don't ship it over the network. It's just like the short circuiting that we saw in HBase. You directly look at it, read it from the same machine that you are sitting on. So this is called bring the query to the data, which was kind of a buzzword also 15 years ago. Still true today. Some people still argue that now you should bring the data to the query, but this is an open debate in some cases. We are done. So I just want to see if maybe just checking the speed. You can tell me, that tells me if I should accelerate, slow down in the future. Normally, I think in terms of timing, we are more or less on time. Okay, so the majority is still between 80 and 99. You should really read the textbook, right? The textbook explains it in written, everything that I told you. I think for the textbook, I used cats instead of Pokemons, but it's just as fun as with Pokemons. Oh, and we have people who understood everything. That is wonderful. So don't hesitate to interact. Those who understood everything, you can explain. To those who understood less than 50%, you can ask questions in the chat. You can ask questions in the forum that we will answer. The TAs are also here for you. I'm here for you. You should solve the exercises. We are trying to get, because there was this Apple Silicon issue with HBase. The TA team is currently setting up 5-2 quiz bis, just for those of you who had these issues, that you still have a chance to get the bonus points, right? Otherwise, it would be unfair that you don't get the points just because of a technical issue. Okay, so thank you very much, everybody. Have a nice week, and I'll see you next week at 8 a.m. Thank you.